Hi folks, we're going to take a look at page 129, number 15. So they give us this function which represents a position function. And they just tell us that k is a non-zero constant, so we treat it as a constant. So part one is to show that the acceleration is constant. Now, first thing I hope you notice is that this is essentially just a quadratic function here. So when we take the derivative of a quadratic, you get a linear, and when you take a derivative of a linear, you get a constant. So we shouldn't be surprised by that. So let's start by finding the velocity, which of course is the derivative of the position function. Now notice the textbook uses s for position, another common variable to use for position besides d, the one that you use in physics that we're using. Okay, so let's start by taking the derivative. So here k is just a constant, so this is just going to be 2kt. This whole expression here is just some constant multiplying t, and the derivative of t is just 1, so this is just plus 6k squared minus 10k, and then of course 2k is a constant, so the derivative of that is 0. All right, next we'll find the acceleration, and the acceleration is just the derivative of the velocity function, or the second derivative of the position function. And so here, this whole thing just is a constant, so its derivative is 0. So my derivative is just 2k, okay, which is a constant because k is a constant. So as we expected, the derivative of this quadratic does indeed give us a constant, so that's part A. And that's the easy part. Part B, I think, is essentially an exercise in algebra. So what they ask us to do is to find the time at which the velocity is 0, and then determine the position of the object when this occurs. All right, so we'll start with this velocity function here and just set it to 0. So we've got 0 equals 2kt plus 6k squared minus 10k. And this is pretty easy because this is just a linear function, and so we can just solve for t using opposite operations. So t is just going to be equal to, so first we bring these expressions to the other side, the constant ones, so that's going to become positive 10k minus 6k squared, and then we'll divide out the 2k to isolate t. All right, and this can be simplified a little more. So let's, this should have been 2k. Sorry about that, because that's the coefficient of t. So I'm just going to factor out a 2k in the numerator, which I can. So here we're left with 5 minus 3k over 2k, and there you go, those reduce, and so the time at which the velocity is 0 is given by 5 minus 3k, where k is that constant that they refer to at the beginning. So now what we have to do is to determine the position at this particular time value when the velocity is 0. Okay, so this is the part that I think is going to be pretty annoying, so we have to find the position at 5 minus 3k. All right, so let's just take that here. It's k times t squared, so 5 minus 3k squared, and then plus this expression here, 6k squared minus 10k times t, which of course is given by 5 minus 3k, and then plus 2k. Okay, and now we just have to do a whole bunch of algebra. So again, this just goes to show you how important it is to have those strong algebra skills when taking a calculus course. So here k times, so we're going to square this. So think of this as 5 minus 3k times 5 minus 3k. So we have 5 times 5 is 25. All right, then we get 5 times negative 3k, which is negative 15. And we have that twice, so minus 30k. And then negative 3k times negative 3k is going to be plus 9k squared. All right. Now we have this product of binomials. So let's take that carefully here. So we have 6k squared times 5. So that's 30k squared. 6k squared times negative 3k. So that's going to be minus 18k cubed. All right. And then we have negative 10k times 5, so that's minus 50k. And then we have negative 10k times negative 3k, so that's plus 30k squared. And then finally we have plus 2k. Okay, so I'm going to write this out with all the like terms together to make the additions, and I'm actually going to write out a term just to make sure I don't make a silly mistake. So here we've got a k cubed term, so that's 9k cubed. Okay, and here we have a k cubed term, so that's minus 18k cubed. So certainly you could skip this step, but sometimes you just want to avoid making a silly mistake. So here we've got minus 30k squared. Okay, here we have plus 30k squared. And then we have another plus 30k squared. Okay, here it looks like I have 25k. Here we've got a minus 50k. And then finally we have the plus 2k. All right, and now we can simplify this here. So this is going to give us negative 9k cubed. These just cancel each other out, so I'm just left with plus 30k squared. And then here we have 25 minus 50, which is negative 25, plus 2 is negative 23k. All right, and there we have our position. So again, this question here was about just applying the fact that velocity is a derivative of position and acceleration is a derivative of velocity. Okay, and then doing a whole bunch of algebra. So the idea here, k just represents a constant, so make sure that any expression that only has numbers and k values is treated as a constant. So that's how I was able to find the two derivatives fairly easily. We confirmed that the velocity, the acceleration of this position function was just a constant. All right, and then we solved for when the velocity was 0, and then we were very careful in determining the position. So whatever that value was, which happened to have a k in there, just became our input to our position function. Okay, that's it for this one.